We should. I think it's somewhere deep in the vault. All right. So, boom, boom. Okay. Playing with graphs here. Okay. The first two sections are really easy and they make lots of sense. Okay. Here's our function. Here's the first derivative. How do we know that that's a maximum? Because of what on this orange line? The orange line is the first derivative. First derivative is slope. When the slope is zero, when the slope is 0, it's a min or a max, right? How do we know it's a max? Well, it's a positive slope to a negative slope. So when the slope goes from positive to 0 to negative, positive slope, 0, negative. Get it? Okay. So if you get that, then which answer is correct? Now, initially I thought, well, because the slope is 0. No, because it could flatten out and have a slope of 0. Okay, so that is not a right answer. It's because it crosses from above to below. If it crosses from above to below, positive slope, 0 slope, negative slope. Okay, so that's how you would answer that. Okay, let's look at the next one. Okay, how do we know that this is a minimum? Well, it crosses here, so it's a negative slope, then 0 slope, then positive slope. Crosses from below to above. Okay, so you'll have a section of those. I mean, those will take like 2 minutes to do, if even. Okay, then you'll have a section. Oh, okay, still on this one, still on this section. The other ones that you'll see is, here's the function. What's the slope, positive or negative, of the blue line? Negative. It's going down constantly, right? It's a negative slope. How do we know that? Well, because the first derivative is always below the what? X-axis. So the first derivative is always negative. That means you'll have a negative slope. Because the first derivative is negative, that'll make a negative slope of the blue line. What? B says this is negative. Just because the original function is negative, that makes the slope negative. It's because the first derivative is negative. Okay, the last one of these. Okay. Why do we know that the blue line is a positive slope? The first derivative is above the x-axis is positive. Okay? All right. Now, here is the original function and the second derivative. So, what is this point called? Point of inflection. Where does the point of inflection happen? Where the second derivative is equal to 0. The point of inflection happens when the second derivative is equal to 0. How do we know it goes from concave up to concave down? Because it goes from a positive second derivative to a negative second derivative. So it goes from above to below. Just kind of like the slope, but now you're dealing with concavity. Okay, let's do that again. Let's do that for this. Why do we know this is concave down? Because the second derivative is negative. That shows that it's concave down. Okay. Why is this point a point of? Ooh, that's not a point of inflection, is it? Okay. Oh, here we go. Why is it a relative maximum based on the second derivative? Now you got to think a little bit more on this one. Why would this be a relative maximum? because this is concave down, and where it's concave down, you're going to have a maximum occur. So, and it's concave down because it's negative here. So when the second derivative is negative, that makes it concave down, which makes a relative maximum. Okay? All right. I think that's the answer. I hope that's the answer. Why is this an inflection point? Because
it's where the second derivative is at 0.
Because it goes from below to above. Okay, because it goes from below to above because it's a negative and then a positive.
What happens if the second derivative bounces?
Like bounces? Then what happens? It's concave down, then it's like a little blip, and then continues concave down. Okay, now these are the painfully difficult ones. Okay, this is what everybody hates in calculus class. Okay, which one is the original function? Which one is the first derivative of it? Which one is the second derivative of it? So this is how I do it. I look at the first one and I say, what's the slopes? I have a negative slope to there, a positive slope to there, and a negative slope. So whatever the first derivative of it is, because it changes slopes here and here. So it's a positive slope here, a negative slope here, and a negative slope here. Is there a function that's negative up to like 1.5, negative 1.5, then positive up to almost 2, basically, and then negative after that? 3 is. Okay? So 3, so if 1 is the original function, then 3 would be the first derivative. Okay? So if 3 is the first derivative, then 2 might be the second derivative. Now, this would do concavity. Okay, so let's figure out, is the original function concave down until like -3? Is it concave? Yeah, it looks like it. Then, is it concave up till a +1? Yep. And then it's concave down from 1 to 3. Yeah, it looks like it. So it looks like it's in that order. 1, 3, 2, which is choice A, which was the right answer. Okay? They're moving tables over there. It's pretty constant. Okay. Now, which one, if we were just going to happen to guess, which one do you think might be the original function? You want to go with 3? Okay, let's go with 3. Let's make 3 the original function. So, I'm looking for something where now we got to look at slopes. The slope from -3 until 2 is negative here, and it's positive here and positive here. From -3 until 2, it needs to be negative. That doesn't happen in either of these, does it? So this is probably going to be the third derivative. Or the second derivative. The third thing in line, but the second derivative. Okay, so what's our next guess? 2? You want 2 to be the original function. So if 2 is the original function, it's all negative slope. So 1 would have to be negative everywhere. Does that work? No. Let's try 1 to be the original function. So it's a positive slope from -2 to 1. So from -2 to 1, it's positive. And so this, if this is the original function, this would definitely be the first derivative of it. Now let's see if this is the second derivative. And if it's not, then this is original, this is the first derivative, and this is the second derivative. Okay? So this is why it makes it so hard. No, it's just guess and check testing of what's going on with slopes. Okay, so this is concave up until about right here. So it should be positive until about right here. This is positive till about right there. Hey, that looks good. And it should be negative after that for quite a while, but we don't know what happens over here. Negative after that for quite a while. We don't know. It must be this. 1, 2, 3. Okay, let's do one more, and then I'll let you get going. Oh, there is a point. It's understanding how slopes of each of these work with each other. Okay, what are we guessing? Where do we want to start?
Start at 2.
Start at 2. We're going to start at 2. If this is our function, then our slope is negative until -4 and positive after that. So I'm looking for something negative until -4 and positive after that, which is this one, right?
Yeah.
So that would be the first derivative of the second one. Now, if this is the first one, the second derivative, it should be concave up, pretty much positive the whole way, and then maybe change to concave down about right there-ish, right? Positive. It might change concavity somewhere over here too. So does that look like this is the second derivative of this? I think so. Concave up from, it should be positive from here-ish till about here-ish. 2.5. So if we go back 2.5, does it change concavity right there? It might change concavity right here because it's got just a little bit of a bend down. I can't write on there. I got to write on here. It's got just a little bit of a bend down here. So yeah, it looks like this could be the second derivative of this. Nice guess, Miles.
That's when you're losing your goal over there.
So 2, 3, 1. 2, 3, 1. Okay? So these are easy. Once you get onto these are easy. But once you get to this, it really takes some work to think through this.